Okay, here we are. We're continuing our discussion of decay and half-life. Um, really, we're looking at decay, what it's all about. We've started talking about the different mechanisms. We're going to talk now about some of the mathematics involved. Unstable radioactive isotopes destroy themselves basically by breaking apart and forming more stable nuclei. This process continues with the new isotopes breaking apart and then those becoming more stable. So basically we can look at a decay tree. And let's start with radium. Radium is element number 88 in the periodic table. It's got a mass number of 226. And if this goes through alpha decay, it breaks up into radon and of course an alpha particle. Radon then breaks up into polonium and an alpha particle. And polonium breaks up into something else and an alpha particle, and so on and so forth. Because each isotope decays in a different amount of time and all isotopes decay in a completely random fashion, really the best way to examine how long they last is to perform a statistical example or statistical analysis of the whole situation. So if we look at an element of radium, and these are all just manufactured numbers, right? So let's say at time 0, we have an activity, so we use a Geiger counter to find the activity, and really we've got 8 decays a second, right? And this would be 8 times 10 to the 13. At 10 minutes left, we then use the Geiger counter again to measure the activity, and we find, oh, now it's down to 4. Which means that really we've gone through half. Basically, this is 1/2 of what it was before, and we call that 1 half-life. So we're down to 50% of the original activity because we started at 8 and now we're down to 4. At 20 minutes, we take our Geiger counter and now we're down to 2 decays per second. And so this is again half of what we had originally, half of a half. So we're now at 2 half-lives have passed. And we're down to about 25% of the original activity. At 30 minutes, we're down to 1. At 40 minutes, we're down to 0.5. And it keeps on getting smaller and smaller by a half each time. And these are what we call half-lives. If we were to graph this activity over time, we find this kind of curve. And we can basically say, oh, this is a special kind of curve that describes this half-life perfectly, and it's an exponential relationship. So here you'll notice that the activity of radium decreases by a half every minute or so, every 10 minutes. Half-life is the amount of time that's required for half of the unstable nuclei in an isotope to decay. We can determine it experimentally using 2 different methods. Either we chemically analyze it to find how much isotope is present at different times, or we can use a Geiger counter to measure the activity over time. A Geiger counter, if you've ever watched any of the old James Bond movies, is kind of like a device that measures activity. It measures how much decay is happening over a certain amount of time, and it kind of clicks when you use it. At least the old ones used to. And if you watch any of those old James Bond movies, you'll see, oh yeah, he uses a Geiger counter a lot. Okay? Activity is basically a way of saying, okay, this is how much radiation is emitted from the nucleus every second. We measure it in becquerels. We could also measure it in other units as well, but becquerel is what we're going to use in this class, and we measure it on a Geiger counter. So what does this look like mathematically? Well, here are our 3 decay equations, and you notice they look exactly the same, except for the letters out front. Okay? So A, this equation, is what we'd use if we're talking about activity. M is what we'd use if we're talking about the mass of the unstable nuclei. And N would be the number of nuclei. Okay, so all of them are basically the same. They represent the same thing, and they all decay in the same way. Okay. T is the amount of time that's gone by, and this right here is the half-life, T 1/2. And half-life is one of those things that's constant for different materials. So strontium would have a different half-life than cobalt, and it would have a different half-life than plutonium. They've all got their own half-lives. And so what we can do is actually, let's take a look at an example for how to solve. So the half-life of strontium-90 is 28 annum. Okay, so that's 28 years is the half-life of strontium-90. If 60 grams of sample of strontium-90 is currently in a sample of soil, how much will be present 90 years later? All right. Well, we know what the half-life is. It's 28 years. We know the original mass. The original mass is 60 grams. And we know how much time is going to pass before we measure again, and that's 90 years later. Well, we'll use, because we're talking about mass, we'll use our equation for mass, which is m equals m naught times 1/2 to the power of t over t half. If you'll remember bed mass, this cannot be done until this exponent is taken care of. So when we multiply this through, we get 90a over 28a. We raise 1/2 to that power, and we get this, 0.1077. Okay, so it's very important that this right here be done first before this multiplication, or else we're not following bed mass and we'll get the wrong answer. And this comes out to 6.46 grams. So after 90 years, when we started with 60 grams, we have 6.46 grams left. And that just goes to show you how 28 years is a really super long half-life. Here's a different question, comes at it from a different angle. The isotope technetium-99 has a half-life of 6 hours. A new sample of technetium with an initial activity of 720 becquerels arrives in a lab. How long will it take the sample to decay to 1/3 of its original activity? So for the most part, when we're doing these kinds of questions, we're going to use exponent laws to solve. But sometimes, and in this example, we may not be able to use exponent laws to solve. So what we say is, okay, we've got a half-life and we get 720 becquerels. We know that the final activity is 1/3 of the initial activity. So we want to find out how long it's going to take for this 720 becquerels to decay down to 240 becquerels. So we'll use, because we're talking about activity, we'll use our equation for activity. We sub in our values, and we get to a problem. And we say, oh, how am I going to find out what this exponent is? Because basically what I've got is I've got 240 over 720 equals 1/2 over t over 6. So really, I've got 1/3 is equal to 1/2 to the power of t over 6. How am I going to determine a number up here that's going to make this true? And this is very difficult. We could do guess and check, and sometimes we could say, oh, is there an exponent that I could use to write this as a base of 1/2? But holy cow, what do I do if I'm in a situation like this? Well, we introduce something called a logarithm. Okay, and you'll learn about these in grade 12 functions, but for right now, all we need to know is how to use a logarithm. And basically, if I take the log of something, and the logarithm is really a button on your calculator, I can actually, it's a really clever way of being able to take an exponent and write it as a coefficient. Okay, so this is one of the laws of logarithms, that if I take the log of anything, I can bring this coefficient down in front and just multiply it out. And like I said, this is really just a button on your calculator. So if I've got this up here, then I can say, okay, let's take the log of 1/3. And you can do this in your calculator, the log of 1 divided by 3. And that's equal to the log of 1/2 to the power of t over 6. Well, using this property right here, I don't have to leave this as an exponent. I can actually bring it down in front. And I can write it as log of 1/3 equals t over 6 times the log of 1/2. And when I put these in my calculator, I get 0.47712, and that's negative. And then the log of 1/2 is negative 0.3010. And hey, this I can handle. This I can do. So what does it give me? 1.581 equals t over 6. Bring the t up and multiply. I get 9.51 hours. Okay, so going through this is a little bit new for many of you. The math is a little bit new. Most of the time we're going to do this using base matching and finding an appropriate power. But sometimes it's pretty easy just to apply the log. But this is kind of like a new concept. So you'll get to see some opportunity to practice this in your homework. Make sure you give it a whirl. But in this case, it'll take 9.51 hours for the sample to decay.